start. Okay. So let's start our class today, Shabab. So inshallah, we'll be ending with the chapter next week, and the remaining chapter, Shabab, will be just kind of theoretical analysis, and they will just go to the application for the hydrogen in the car, acid car. We'll talk about fuel cells. So just it will be a kind of, we can say it will be a kind of discussion, not really we are presenting something new or something. So inshallah we'll end up with this chapter. We still will have inshallah next week to end up with this. Then inshallah we can have additional 2 classes in the last chapter. It will be discussion. طيب inshallah today we'll continue our talk. Last time we talk about started our talk about the engine performance. Last time we talked about how we calculate the displacement volume in terms actually of the engine CC multiplied by the number of cycles per second, and how to calculate the mass flow rate of air per cycle in terms of the displacement volume and multiplied by the density of air. From mass flow rate of air, we have learned how to get the mass flow rate of fuel through the fuel to air ratio. And we learned about the combustion efficiency, because we cannot make sure that all of the fuel will be converted to heat, all the chemical energy will be converted to thermal energy. That's why we have to define any internal combustion engine with a combustion efficiency. However, in all of the analysis, engine performance analysis, we assume that the combustion efficiency is equal to 1. So we assume that the heat added inside the piston is equal to m dot fuel multiplied by the lower heating value, which is the chemical energy of the fuel. Also, we'll talk about the difference between brake power and the indicate power. We said the indicate power is the power that we can get from the indicator diagram, like the PV diagram, like what we have learned in chapter 5. Indicated power is equal to integration of PDV, which is the network, and we have to multiply by the number of cycles per second, then we can get the indicated power, or the rate of power generated inside the piston. This power generated inside the piston, we said this power we cannot measure it, but just we can get it from the indicator diagram, and actually based on the theoretical analysis we can calculate this indicated power. We can do the integration and then we can calculate the indicated power. But actually we don't have a measure, experimental technique in order to measure the indicated power of a piston, but we can measure the brake power. Brake power is the final power on the crankshaft. We have a rotating shaft. We said this last time that we can use a dynamometer. This dynamometer, we can use it. We said we have a crankshaft that can rotate inside actually outer casing. This casing in between the impeller and the casing, we can have water or any fluid. That's why we call it hydraulic dynamometer. Once the rotor starts rotating, the water will try to rotate and the outer casing will be started tilting in the same direction. Then we can return it back to its original position in the vertical position by adding some weight here at a certain distance b. Then we can calculate the torque multiplied by the RPM of this shaft. Then we can calculate or we can measure the brake power in this case. And we said, Shabab, the difference between the brake power and the indicated power is the friction power. And we said also that the friction power includes the pumping work, which is the work applied on the piston coming from the crankshaft and supplied to the piston in order to draw the air or the charge during the intake stroke and also during the exhaust stroke. So during the intake and the exhaust stroke, the piston just need power in order to move, just to move down to suck the air and move up in order to exhaust the gases. This is pumping work, and we can consider it as a part of the friction loss power. The friction loss power also includes the rubbing friction losses, the friction losses between the piston as it is moving inside the cylinder. So we should have friction between the piston and the cylinder wall. Also, Shabab, we have mixing between gases, and this is actually a totally irreversible process. So we have friction losses in the gas phase itself, between the molecules, even we have friction losses. So all of this we can call those are rubbing friction, which are also part of the friction loss power. In addition, Shabab, we can consider all of the power required to running all the accessories inside the engine, including the fuel pump, water pump, recirculating cooling water pump, fan actually for the radiator, the compressor in case when we have air conditioning, and we should have air conditioning. So the compressor for air conditioning take part of the power of the crankshaft, part of the brake power. Also, if the engine supercharged, in this case, the compressor take part of the brake power or the output power in this case. all of the power required to run the accessories, we can also consider them as part of the friction loss power. So the difference between indicated power, which is the power generated inside the piston, and the power, the final power in the crankshaft, we call it as actually as the friction power. And as we said here, Shabab, this friction power is equal to the rubbing friction losses, the friction losses between the piston as it is moving inside the cylinder, and the piston and the cylinder, and also we have friction between the molecules in the gas phase inside the piston itself. Also, it is equal to the power required to run the accessories, all of the accessories within the engine, like the fuel pump, as we said, compressor, water, cooling water recirculation pump, all of these are accessories which take part of the output power. So the friction loss power is equal to the rubbing friction losses plus the accessories plus actually the pumping work, which is the work that is required to drive the piston during the intake and the exhaust stroke. All of this, Shabab, can sum up actually to the final friction loss power. And we see the difference between the indicated power, which is the power generated inside the piston, and the brake power should equal to the friction loss power in this case. So the indicated power is equal to the final brake power plus the friction loss power. If you look at the sequence, Shabab, of the energy conversion for any internal combustion engine, through the intake valve here, we have the charges coming. So it should have the chemical energy of the fuel, which is equal to m dot fuel multiplied by the lower heating value of this fuel. This fuel will be coming inside the piston and inside this combustion chamber. So the combustion chamber, Shabab, is the minimum volume between the piston heat and the cylinder heat, which is usually defined by the clearance volume. So usually the combustion takes place inside this clearance volume, and it will result in a heat transfer in this case. So the chemical energy, which is the energy stored in the fuel molecules, will be released actually in terms of the thermal energy in this case. And this conversion process, Shabab, we should have a combustion efficiency. Combustion efficiency, which is equal to Q dot added divided by m dot fuel multiplied by the lower heating value. And this is actually the efficiency of combustion. As we said, we cannot guarantee actually that all of the fuel, all of the chemical energy will be released and be converted to thermal energy in this case. But in most of the performance analysis of any engine, we just assume this combustion efficiency is equal to 1. Okay, so we assume all of the chemical energy will be converted to heat. And this heat, once we have heat here at lower volume, minimum volume, so this will result actually in increase in pressure and increase in temperature as well. This increase in pressure and temperature will press the piston down, and it will apply indicated power. Indicated power in this, Shabab, in this case is a mechanical power, okay, that will move the piston down. So the indicated power is the power that moves the piston actually down in terms of reciprocating motion, and at the end we have a connecting rod that will be connected to a crankshaft, and at this crankshaft it will be rotating at a given RPM, in is the revolution per minute of the crankshaft, and it can deliver us at the end actually the brake power. The difference between the indicated power here and the brake power is the friction loss power. And we said the friction loss power is the rubbing friction losses plus all of the power required to run all of the accessories of the engine, plus the pumping work of the piston during the intake and the exhaust stroke. And we have related, Shabab, also the brake power and the indicated power through the mechanical efficiency, because indicated power is a mechanical power. Brake power is also a mechanical power, but indicated power results actually in reciprocating motion. Brake power is actually just a rotary motion. When you convert from a mechanical power to a mechanical power, we have to define a mechanical efficiency. And this mechanical efficiency will give us indication about the friction loss power, which is equal to the brake power divided by eta mechanical for the engine is the difference, the ratio of the brake power divided by the indicated power. This brake power, Shabab, at part load, the throttle valve here will be just through the intake manifold here. The throttle valve actually will be just opening a small opening in this case. So the amount of air to the engine, the pressure will be reduced, and the mass flow rate of air will be reduced, and accordingly the mass flow rate of fuel will be reduced, and the power of the engine will be reduced. That means at part load condition, and we have said this last time, the mechanical efficiency of the engine will be reduced. Here you can see at part load condition, usually the mechanical efficiency will be reduced, At wide open throttle, at full load condition, the mechanical efficiency almost about 90%. So usually we can have a kind of 10% of the losses. But as you increase the speed, يا شباب, at the maximum rated speed, as you increase the speed, in this case, the friction loss power will be increased, okay? And that's why the mechanical efficiency will be reduced up to 75% at the engine rated power. So when the engine is running at its rated speed, which is a high speed, the friction loss power will be increased. In this case, friction loss power increased. That means the brake power will be decreased and the mechanical efficiency will be decreased. And you have to know, Shabab, that the friction loss power is proportional actually to n square. So you can see here, as we increase n, the increase in the friction loss power is proportional to actually the square of the RPM of the engine. Okay, you can look here, Shabab. We have discussed this figure last time. Where is it? We have discussed this figure last time. As you can see, Shabab, when you increase the RPM, if you are running your car, but look here at 6,000 RPM or 6,500 RPM, you will find this is the maximum rated power. If you increase the RPM of the engine over 6,500, which is very high, usually when you drive your car, it should be around 2,500, 3,000 RPM. But if you want actually to get the rate of this engine, when you increase the RPM, that means you are consuming more fuel. So that means we are increasing the brake power. And also the indicate power is increasing, and the mechanical efficiency, it's okay, will be increasing. But there is a limit. When you reach this limit, which is the rated power at almost about 6,500 RPM, that should be the rated power. If you increase the speed more than this, the friction loss power, the rate of increase of the friction loss power will be more than the rate of increase of the brake power. Because when you increase the RPM, you are consuming more fuel. More fuel, that means you are generating more indicated power. Okay? This indicated power is equal to the brake power plus the friction loss power. Both of them should be increased, but at higher RPM, more than the rated power, when you run the engine at a speed higher than actually the speed of the rated power, at the rated power, the increase of the friction loss power will be much more than the increase in the brake power. So that means in this case, finally, the brake power will be reduced of the engine. Okay, and this is the idea. The friction loss power is proportional to actually to n square in this case. طيب, how we can calculate? And we said, Shabab, also the mechanical efficiency, this value should equal to 0. Under which condition, Shabab? Under which condition we can get the mechanical efficiency is equal to 0? When it should equal to 0, Shabab? When the brake power is equal to what? Is equal to 0. But when we can get the engine of brake power equal to 0? Under which condition?
With the car not moving.
What you said?
When the car is parking.
Yeah, exactly. Not really when it is in the parking mode, but the engine is running. Like, Shabab, we call this condition, Shabab, the idling condition. When the engine is running, but the car is not moving, like when you stop at the signal and in the parking mode. Okay, so in this case, the engine is running, but we don't have output power. All of the brake power in this case, Shabab, is just consumed and converted to the friction loss power in this case. And in this case, at idling condition, the mechanical efficiency of the engine should be a value equal to 0. Right, how we can measure, Shabab? We said the indicated power is the power from the indicator diagram, from the PV diagram, which is function of integration of VDV, and we can multiply by the number of cycles per second, then we can get the indicated power in this case. But we cannot measure the indicated power. But we said we can measure the brake power through a dynamometer like hydraulic dynamometer or electric dynamometer. But we need also to measure the friction loss power. How we can measure the friction loss power? We said at the idling condition, in this case the brake power, output brake power, all of it will be consumed in the friction power. Or sorry, the indicated power, the generated indicated power will be just consumed in the friction loss power, and in this case the brake power at the end should equal to 0 under this condition. Okay. But to calculate the friction loss power, we can run the engine at the idling condition. When we have all of the indicated power is just converted to a friction to friction loss power in this case. We have different methods. We can have direct motoring. We can run the engine under the idling condition until it reaches actually the steady state condition in terms of the temperature of the cooling water and the temperature of the cooling oil until it reaches the steady state. Then in this case, while firing the engine, running the engine using the fuel. And then we can just disconnect the fuel and then we can connect it to an electric motor. This electric motor will be driving the engine at the same RPM. This friction loss power is fixed when the RPM is fixed. So it is function of the RPM of the engine. So if I need to calculate the friction loss power, I am talking actually at a fixed engine RPM because this friction loss power is function of the RPM of the shaft. So we can disconnect the engine, just actually turn it down, disconnect the fuel, connect the crankshaft to an electric motor in this case, run the engine at the same speed, then in this case the electrical power will equal to the friction loss power in this case. So this is one method. Another method is called actually the Williams line. Williams line is a kind of experiment in which we can run the engine at different loading condition, and each time we can calculate the mass flow rate consumed, the mass flow rate of the fuel consumed by the engine at a given brake power. Each time we record the mass flow rate. We said brake power we can measure using a dynamometer. Okay, but how we can measure the mass flow rate of fuel? Usually this is the fuel tank. We can just observe one very old method to calculate the mass flow rate. Fuel actually is consumed by the engine from the fuel tank, and the level of this tank actually is changing with time, depending on actually the mass flow rate of the fuel consumed by the engine. So we can just observe, record the time until we have actually a certain consumption level, certain volume of the fuel is consumed. Then in this case, we can just calculate the mass flow rate of the fuel. And at a given RPM, as I told you, to calculate the friction loss power, we have to fix the RPM. At a given RPM, we can measure this brake power. Then we can change the brake power. How we can change the brake power? Let's say we need to reduce the brake power. Power of the engine is related to what, or the engine load. Engine load is function of what, How to change the brake power. What you do in your car if you want the car to move with higher power, higher RPM? What should you do? If you need the... Yes, Hassan?
Throttling valve.
Exactly, the throttle valve in this case. Here in the intake manifold, we have the throttle valve, which is connected to the accelerator pedal, which you just press by your leg here. So when you need more power, you will try to open this throttle valve a little bit more. Then in this case, it will allow for more air. If I need to reduce the brake power, I will just raise my leg here. Then in this case, we can reduce, just close the throttle valve partially, and we can reduce the brake power. Anyway, in the Williams line at fixed engine RPM, we can change the brake power, and each time we can calculate the mass flow rate of fuel. And we can just fit this relation. Fit it to a straight line in this case. If you look at this point, this point at which actually we do have the mass flow rate of fuel at the idling condition, at which the condition at which we have the brake power is equal to 0. So this is the mass flow rate of the fuel consumed under the idling condition, when the engine is running but the car is not moving. But we say the friction loss power should equal to the indicated power under the idling condition. Okay, and in this case the brake power is equal to 0. If I extrapolate actually this line here and get the intersection with the horizontal line, this difference we can call it actually, should be equal to the friction loss power. So the friction loss power, or the friction power, is the power corresponding actually to the idling condition. Okay, and this mass flow rate of the fuel is the mass flow rate of the fuel consumed in order to be just overcoming the friction loss power at a given engine RPM. Okay, so Williams line is an experimental method in which we record the mode of fuel again as the brake power, just fit it to a straight line. Then in this case, we can just extrapolate this line, and the intersection with the x-axis in this case should equal to the friction loss power. Another method, or a third method to calculate the friction loss power, which we are concerned with here, is the Morse test. Morse test is a kind of nice experiment in which actually we have a multi-cylinder engine. This multiple cylinder engine, this test شباب Morse test can be applied for gasoline or diesel engine. It states like if you have multiple cylinder engine, let's say we have 4 cylinder spark ignition engine. So in each cylinder, let's say we have a spark plug here, spark plug 1, spark plug 2, spark plug 3, and here we have a spark plug number 4. And the piston, here are the pistons inside this cylinder. Each cylinder, we should have a piston. Usually, شباب, if you have 4 piston cylinder, 4-cylinder engine, you will have two. Usually, we have 2 cylinder. Each 2 cylinder are moving with each other, but they are doing different stroke. So one here should be doing the exhaust stroke, and this one will be going out during the compression stroke. But they are moving together, and the other 2 are moving together. In order, just because all of them are connected to the crankshaft here, in order just to reduce the stresses applied on the crankshaft and just to create a kind of balance. So those are the connecting rod, and at the end we should have the brake power at the output, actually crankshaft, which should be running at a given RPM. In this experiment, I need to calculate the friction power, so I will just fix the RPM of the engine at a given RPM for this engine. So in this case, شباب, we can say for the whole engine, for the 4-cylinder, the indicated power for all cylinder from 1 to 4 should equal to the brake power for all cylinders from 1 to 4 plus the friction loss power. So this is actually considering all cylinders are running. Type, let's disconnect actually this spark plug. So this cylinder will not be involved in this case. We are not applying actually spark here, we are not generating combustion, so we don't get actually brake power out of it. Type, once you disconnect this cylinder, what will happen to the RPM here? And the brake power? It will be what? It will be reduced because I just cut one cylinder off. So the RPM will be reduced and the brake power will be reduced. So in this case, I will just press on the throttle valve, try to widen the opening of the throttle valve, supply more air, supply more fuel, and then the brake power will be increased in order to keep the N constant. In all cases, شباب, we have to keep the RPM of the crankshaft constant. Then we have increased the mass flow rate of air, mass flow rate of fuel, N has been kept constant. In the second step, when we just disconnect the spark plug 1, in this case, the indicated power for cylinder 2, 3, and cylinder number 4 should equal to the brake power for the cylinder 2, 3, and 4 plus the same friction loss power. When I just disconnect one cylinder, its piston is moving, going up and down with the crankshaft, but we don't have power generated or combustion. So it is involved already in the calculation of the friction power. So the indicated power for the remaining cylinder 2, 3, and 4 should equal to the brake power for cylinder 2 and 3 and 4. We don't have indicated power or brake power for cylinder 1, but plus the same friction loss power. Okay, if you look at those 2 equations, if I just subtract the 2 equations, so the indicated power for all cylinder minus the indicated power for cylinder 2, 3, and 4, that should represent the indicated power of the cylinder number 1, which we have cut the spark plug in this case, 4. And the difference here will equal to the brake power for all cylinder from 1 to 4 minus the brake power actually for cylinder 2, 3, and 4. So when we just cut the spark plug and widen the opening of the throttle valve to retain the same RPM, in this case we can also using a dynamometer, we can measure the brake power for the remaining cylinder. So this term we can measure, and also we can measure the RPM. Okay, so at a given RPM, until we retain the same RPM, we can measure the brake power for the remaining cylinder. And in this case, we can get actually this equation. And initially, we have measured the brake power for all cylinders at the same RPM. So now we are able to calculate the indicated power for cylinder number 1. And like this, I will just reconnect the spark plug number 1. And I will disconnect the spark plug for the second cylinder. And in this case, also I can get the same way the indicated power for the second cylinder, cylinder number 2, will equal to the difference in brake power all for all cylinder from 1 to 4 minus the brake power for the remaining cylinder. I'm talking here about cylinder number 2. So the remaining will be 1, 3, and 4 in this case. We can measure the brake power for the remaining cylinder, and we have measured the brake power for all cylinder or cylinder from 1 to 4. And in this case, I can calculate the indicated power for the second cylinder. Okay, like this we can do and calculate the indicated power for the third cylinder and the indicated power for the fourth one, and then I can sum them up all. Then I can calculate the indicated power all. Okay, is it a شباب? So when I sum them up, I can calculate the indicated power all, and I have already measured the brake power for all cylinder at the beginning of the test at a given RPM. Then in this case, I can just calculate the friction loss power, which will be the difference between the summation of all indicated power for all cylinder minus the brake power for all cylinder. So for this test, شباب, just we need RPM sensor and we need a dynamometer in order to measure the brake power, because each time when we cut the spark plug of one cylinder, in this case I have to widely open the throttle valve in order to increase the mass flow rate of air and fuel. Then we can increase the brake power and increase the RPM until we get the same value, NS constant. And each time we measure the brake power. So when we cut cylinder number 1, when we measure the brake power at the same RPM, will be brake power for the remaining cylinder, cylinder number 2 and 3 and 4. Okay, but the friction loss power in all cases will be the same, because when we cut the spark plug of one cylinder, the piston still is moving up and down. Okay, but we don't have combustion. So it's actually participation in the friction loss power is involved. So when we subtract the two equations, then we can get actually the indicated power for the cylinder that actually we have the spark plug for. And then we can sum up all the indicated power to calculate the indicated power all, and that should equal to the brake power all, which we have measured already using a dynamometer, and then we can get the difference to get the friction loss power. Is that clear, شباب? Is the idea of this test clear? So Abdullah, Rida, is that clear?
Definitely.
So this is يا شباب a kind of nice test by which we can measure the friction loss power in this case. Okay. But let's move to another topic and see the sequence. We have to look at the performance of the engine. We have to look at different efficiencies. We have to calculate the efficiency of the engine. But which kind of efficiency? We said here, we have the first input power to the engine here, شباب, is the chemical energy. Chemical energy, which is equal to M dot fuel multiplied by the lower heating value of the fuel. This is the chemical energy, which will be converted to a thermal energy in terms of heat transfer. And based on that, we have to define a combustion efficiency, which is the heat transfer Q dot added to the engine divided by M dot fuel multiplied by the lower heating value. As I told you, in most of the cases, we consider the analysis of the engine based on a combustion efficiency equal to 1 in this case. So first of all, we have the chemical energy, which is M dot fuel multiplied by the lower heating value. This is converted actually to the thermal energy, which is Q dot added. And in this case, we have to define the combustion efficiency, which is Q dot added, the thermal heat divided by the chemical energy, which is M dot fuel multiplied by the lower heating value. But this Q dot added will be converted to a mechanical power inside the cylinder, which is the indicated power. So this Q dot added is converted to the indicated power. Indicated power is a mechanical power. So we have thermal power is converted to a mechanical power. So in this case, in between, I have to define a thermal efficiency for the engine in this case. Okay, and this thermal efficiency should equal to the output mechanical power divided by the input thermal energy in this case, which is Q dot added. In case when we have either combustion, this term is equal to 1, so Q dot added will just equal to M dot fuel multiplied by the lower heating value. And at the end, this indicated power should be converted on the crankshaft to a brake power. Indicated power and the brake power are mechanical power. So in this case, we have to define the mechanical efficiency, which is the ratio between the indicated power divided by the brake power. Type this thermal efficiency is the output mechanical energy divided by the input thermal energy. But which output mechanical energy? We have two mechanical energy. We have indicated power inside the cylinder, and we have brake power on the crankshaft. And that's why, Shabab, we have two definitions for the thermal efficiency. We have one, which we call it eta indicated thermal, which is equal to the indicated power divided by Q dot L. And we have another thermal efficiency. We call it eta brake thermal, or overall efficiency. Why we call it overall, Shabab? Because it considers the final output divided by the initial input. Okay, we call eta brake thermal. We call it the overall efficiency. So we call it eta overall, or we call it eta thermal in general. So if you have an engine and somebody just tell you the thermal efficiency of this engine is equal to this value, so he should be talking about the eta brake thermal, because he should be talking about the final outcome. But we have another important efficiency, which is eta indicated thermal. We have learned how to calculate this efficiency based on the cycle representation on chapter 5. We have considered for the fuel air cycle and also for the air standard cycle, we have calculated the indicated thermal efficiency based on the Otto cycle, diesel cycle, and dual cycle. And also in the fuel air cycle, we have calculated the indicated thermal efficiency based on the indicator diagram. Okay, eta brake thermal is the overall efficiency, which just represents the ratio between the brake power divided by Q dot added in this case. And what is the ratio between both of them, Shabab? The ratio between eta brake thermal and eta indicated thermal should be representing what? When I just divide both of them. Eta brake thermal is brake power divided by Q dot L. Eta indicate thermal is indicated power divided by Q dot L. When I divide them together, so Q dot L will be going, so it will be brake power over indicated power. So the mechanical efficiency is the ratio between eta brake thermal divided by eta indicated thermal. So let's look in deep how we can define those two efficiencies, the thermal efficiency of the engine. We said eta indicated thermal, we have calculated already based on chapter 5, based on the analysis of the PD diagram, which is equal to the indicated power divided by Q dot L. But in most of the cases, Shabab, and this also, Shabab, we can say indicated power, how we can define it, Shabab, based on the indicator diagram. We said the indicated power is the network that we get actually from the indicator diagram, which is equal to the integration of BDV, which represents the network, multiplied by N divided by R by 60, which is the number of cycles per second. Then we can calculate the indicated power in this case. And it is the output power. We used to define, Shabab, the indicated thermal efficiency in chapter 5 as work.net. This is, Shabab, what we call actually work.net in chapter 5, which is the indicated power. So work.net is the same as Q.net. So it is equal to 1 minus Q dot rejected divided by Q dot added in this case. This is how we define the eta indicated thermal indicated power divided by Q dot added, or it is equal to this indicated power, Shabab, is the work dot net, which is integration of BDV. It is equal to the same as Q.net. Then we can define it 1 minus Q rejected divided by Q.L. But in case if we have eta combustion is equal to 1, if the combustion efficiency is equal to 1, and this will be the case in most of the analysis, then we can reduce just the Q dot added should equal to M dot fuel multiplied by the lower heating value of the fuel. And based on that, Shabab, we can define the eta indicated thermal as equal to the indicated power divided by M dot fuel multiplied by the heating value. So eta indicated thermal will equal to the indicated power divided by M dot fuel multiplied by the lower heating value in this case. And it is the same, Shabab, equal to 1 minus Q dot rejected divided by Q dot added from this engine. And eta brake thermal will equal to the brake power divided by m dot fuel multiplied by the lower heating value. So this is how we can define the thermal efficiency. We can define it based on the indicated mechanical power divided by m dot fuel by lower heating value. We call it eta indicated thermal, or we can define it as overall efficiency or overall thermal efficiency in terms of eta brake thermal. It should equal to the brake power divided by m dot fuel multiplied by the lower heating value, and the eta mechanical is the ratio between eta brake thermal divided by eta indicated thermal. And this brake power is the power on the crankshaft that should equal to the torque multiplied by omega, which is 2 pi n divided by 60. So if I give you the RPM of the shaft, I give you the torque of the engine, then in this case you can calculate the overall brake power of this engine in this case. As I told you, this brake power we can measure. We can measure through measuring the torque of the engine. So most of the problem you will find the torque should be given because we can measure it. Also the RPM can be measured. Then in this case we can calculate the brake power. If we have the brake power, we have mass flow rate of the fuel, then we can calculate eta brake thermal for the engine. Okay. But usually the analysis starts from the fuel air cycle. I can give you fuel air cycle like the auto cycle, like the homework you have followed. You have going through the cycle until you have calculated the eta indicated thermal, which is 1 minus Q rejected divided by Q added. Once you calculate eta indicated thermal, then you can relate actually the indicated power equal to indicated power divided by m dot fuel by lower heating value. And then if mechanical efficiency is given, we can calculate eta brake thermal. From eta brake thermal, we can calculate the brake power, and then we can continue the analysis of the engine. So as a matter of fact, for the whole course, we can give you a kind of practice problem like the homework problems that you have done. You have calculated the indicated thermal efficiency. Then from this point, you can continue throughout this chapter to calculate all of the performance parameters of the engine. At a given RPM, we are able to calculate the mass flow rate of air, which is equal to the density of air multiplied by the displacement volume. Then we can give you the fuel to air ratio to calculate the mass flow rate of fuel at a given RPM. Calculate the indicated thermal efficiency using the cycle analysis. Go through the process from 1, 2, 3.3, and 4, following the processes of the Otto cycle or the fuel air cycle. Calculate the indicated thermal efficiency. We should give you, in this case, I can give you the mechanical efficiency. So at the end, you can calculate the brake power at a given RPM. Because when we change the RPM, the mass flow rate of air to the engine will be changed in this case. And you can just go and look at this performance curve. You can just plot this curve. So I can give you a problem like that, but I will not do because we don't have much time. So at a given condition, at a given RPM, you can calculate the mass flow rate of air, from which you can calculate the mass flow rate of fuel using the fuel to air ratio. Through the cycle analysis, from the inlet condition pressure and temperature to the cylinder, you can go, and using chapter 5 analysis, we can calculate the indicated thermal efficiency and so on until you calculate based on the performance parameters, the brake power, and at the end you can plot the brake power against the RPM. It changes the RPM, the mass flow rate of air will be changed. You have to do the same calculations that you have done, especially in the last homework. And again, you will be calculating the brake power. So actually, you can generate this performance curve for any car, for any engine, not car, any internal combustion engine. You can just generate the performance curve. So when you buy a car or something, if you look at the catalog, you will find the engine map. Engine map will give you the brake power as a function of RPM, and also will give you the brake specific fuel consumption or the mass flow rate of fuel. And this is based on this analysis. This is how we can get actually this performance map. Also, you can plot this curve. You can plot the torque against the RPM. Okay, but this is not we'll go in deep into that. So this is how we can define the brake thermal efficiency and the indicated thermal efficiency, and the ratio between both of them, brake thermal and the indicated thermal, can give us indication about the mechanical power, mechanical efficiency. And here how we define the brake power, which is equal to the torque multiplied by the omega in this case. Another very important performance parameter, in addition to the thermal efficiency either indicated or brake thermal efficiency, because we have two mechanical power. One of them is the reciprocating mechanical power of the piston inside the engine, which is the indicated power and the other is the rotating crankshaft bar. Okay. طيب, all the parameters you will see will have both of them. One is brake, one is indicate, because we have two mechanical bar in this case. One indicated bar inside the cylinder, and the other in the crankshaft, which is the final bar. Like this, we have the specific fuel consumption. Which is actually the amount of fuel, the mass flow rate of fuel consumed per unit power output. Usually it is calculated in kilogram per kilowatt hour. This is how we can define the specific fuel consumption. And the specific fuel consumption is equal to M dot fuel per unit power output. But which power? It can be actually the indicated power or the brake power, and that's why we have two definitions for the specific fuel consumption. We have indicated specific fuel consumption, which is equal to the indicated power, M dot fuel divided by the indicated power, or we can define another parameter, which is more realistic one, brake specific fuel consumption, which is the one already defined for any engine, because it is representing the overall or the final power of the engine. It is equal to M dot fuel divided by the brake power of the engine. And the ratio between both of them is what? Is the mechanical efficiency. But mechanical efficiency in this case will equal to indicator specific fuel consumption divided by brake specific fuel consumption. And this is a very important parameter regarding the economy of any engine. We have to know about actually the amount of mass flow rate of fuel consumed in order to produce actually unit power output. Usually we are concerned with the brake specific fuel consumption, which is equal to the mass flow rate of fuel consumed per unit brake power output of this engine. Usually it is not represented this way. Usually if you go to the market and try to buy a car, he will just tell you something else. He will tell you about the car mileage, which is the number of kilometers that the car can travel per unit liter of the fuel. So usually when you go to buy a car, he will say this car can run for 100 kilometers using, let's say, 6.7 liter of fuel. Another car can run for 100 kilometers at average vehicle speed. This is at average vehicle speed. At a given speed of the car, this car can travel 100 kilometers using 6.7 liter. Because when we change the vehicle speed, that we are changing the RPM. That means we are changing the friction power in this case. So when you say car mileage, the amount of kilometers that the car can travel for a given liter of fuel, that should be at a given average vehicle speed. Okay, at a given RPM of the crankshaft. Another car, and this is a very important parameter in comparing actually different engine or different car. He can say actually this car can travel for 100 kilometers, let's say, for 10 liters of the fuel. So that means actually this car is consuming less fuel, less amount of fuel for the same traveling distance in this case. If you need to calculate the car mileage, we call it car mileage, which is equal to the distances that the car can travel at a given, for a given fuel flow rate, which is equal to the average vehicle speed divided by the volumetric flow rate of the fuel. Average vehicle speed divided by the volumetric flow rate of fuel, so it is average vehicle speed divided by V dot, which is M dot fuel divided by the density of the fuel. If I multiply it here by the brake power, up and down, so it will be M dot fuel here divided by the brake power, which is the brake specific fuel consumption. So this term will equal to raw fuel divided by the brake specific fuel consumption multiplied or divided by, can take the brake power output, so it will be brake power divided by the average vehicle speed. And this is how we can define the car mileage, is equal to the density of the fuel, which is gasoline fuel in case actually of gasoline engine, divided by the brake specific fuel consumption. And this term is divided by another term, which is representing the brake power produced by the engine at a given average vehicle speed. This term, the brake power at a given average vehicle speed, is just can be calculated from the field test actually of any car. So before releasing any version of the car, they have to run this car at the average vehicle speed and they have to calculate the amount of fuel consumed in this case to run actually this car at this average vehicle speed to run actually a distance. Usually in the market, you will find this is the usual distance that they compare between the different cars. They said actually this car can be running the 100 kilometer for only 6.7 liter. But you have to check about what is you have to check about which speed, okay? So this is a very important parameter because maybe you find another car actually that can run the 100 kilometer and they consume 10 liter, not a kind of 7 liter or 6.7 liter, but maybe this car is better than this car because maybe this car actually is running at higher RPM, and in this case, as we increase the RPM, the friction losses will be increased in this case. So that means it can run the 100 kilometer in a shorter time, okay? And this is another factor. But if we have the two cars are running at the same average vehicle speed, same field test has been done, the same average vehicle speed, usually we can do this for the same company, like Nissan or Toyota, we have different cars. So usually they have this field test actually is almost fixed for all types of car, all version of the car. So if you compare Toyota, let's say Fortuner with another Toyota Yaris or Corolla or any other version, so in this case, they should have the same average vehicle speed. Because the same companies, they should apply the same test. So when you compare them and you find one of them can consume less amount of fuel than the other, that means actually the one consuming less amount of fuel should be better in this case for the same 100 kilometer. But if we change the company from Toyota to Nissan, let's say, so in this case, the average vehicle speed may be different. So don't say actually when you see those numbers are different, you don't say actually that the lower value is much better in all cases, because it depends. It should be better than the greater value in case if we have the same average vehicle speed, okay? But otherwise, we have to look at actually in order to have fair comparison. In this case, we have to have the same average vehicle speed, or we should have the same brake power divided by average vehicle speed. Okay, so you should have the full definition here. Okay, so this term car mileage equal to raw fuel divided by brake specific fuel consumption, and this divided by the brake power produced at average vehicle speed. Is it clear, Shabab? Is that clear?
So we can only use the average mileage.
So always the car mileage in order to compare between the different cars.
Okay.
But Shabab, as I told you, we have to consider the whole. This is how we define the car mileage. It is density of the fuel. The two cars should be using the same fuel, so it should be the same density of the fuel. But they should have different brake specific fuel consumption. But they should have the same brake power per average vehicle speed. So in this case, if this term is constant, brake power over average vehicle speed is constant, they are using the same fuel, this is constant. So now we are comparing the brake specific fuel consumption. And this is a realistic term. So yeah, Shabab, car mileage may be misleading because we may have different value of brake power over average vehicle speed. But usually the brake specific fuel consumption is a clear comparison, because it gives actually the value of the mass flow rate of fuel consumed per unit brake power. So you have to look at the details of the specs. If you compare two engines, look at this term. The ones that have lower brake specific fuel consumption, that means actually this is the better one, because it is consuming actually less amount of fuel in this case. Okay. So, and also, Shabab, the mechanical efficiency is the difference between the indicated fuel specific fuel consumption divided by the brake specific fuel consumption. Another parameter, Shabab, which is the mean effective pressure. You will find this parameter is a very important performance parameter, which we call it the mean effective pressure. We talk about the mean effective pressure, Shabab, in chapter 5. We have defined the indicate mean effective pressure. We said this is equal to the network divided by the displacement of volume, or it can be defined in terms of power. It can be network in terms of power. It is representing the indicated power divided by the rate of displacement of volume, which is V dot displacement. And it is defined as the fixed pressure It is not a pressure, شباب. It is just, we call it pressure because it is the power per unit displacement. So its unit at the end will be in bar or kilopascal. So we call it pressure. But it is defined, شباب, as the pressure, the constant pressure that can give actually the same network out of the actual cycle. So if you look at the actual cycle on the PV diagram, so if this is the top dead center and this is the bottom dead center, if you look at the pressure variation starting from the intake stroke, usually the pressure increase, and then we have expansion at the end, we should have the exhaust and the intake stroke. And we have defined, شباب, the network of this cycle by this area. So this is the network for the actual cycle. Okay, and as you can see, the pressure is varying through this cycle. From one cycle, from one stroke to another, we have different variation in pressure. The indicate mean effective pressure, or the mean effective pressure in general, is the value of the pressure, the constant pressure, if this cycle to be driven at constant pressure. This constant pressure, we call it the mean effective pressure. In this case, this constant pressure will result in a work, which is the area under the curve on this diagram. This area should be the same as work in it. So the work in this case should equal to integration of BdV, should equal to the same area for the network area represented by the actual cycle. So in the actual cycle, the pressure is varying through the cycle. And this area, شباب, is representing the network for the actual cycle. But if this cycle is to be driven at a constant pressure, we will call this pressure as the mean effective pressure. The area under the curve on the PV diagram, which should be representing the work, this constant pressure should result actually in the same area under the curve or the same value of the work in it. That means, شباب, if we have an engine with higher mean effective pressure, that means actually in this case this engine have higher what? Have higher work in it, because it is the fixed mean effective pressure or the fixed pressure that can result in the same area under the curve on the PV diagram, or the same work in it, or the same work equal to, that is equal to the work for the actual cycle in this case. And the indicate mean effective pressure, or the mean effective pressure in general, can be defined as, we can say, indicate mean effective pressure, which is equal to the indicated power divided by V dot displacement, the rate of displacement volume. Or it can be defined in terms of the brake power, and in this case we call it the brake mean effective pressure, which will equal to the brake power divided by V dot displacement, or the rate of displacement volume. V dot displacement, which is the displacement volume, by over 4d square L multiplied by the number of cylinders Z, multiplied by the number of cycles per second, which is N divided by R, multiplied by 60 in this case. Okay, so this is the V dot displacement. This indicated bar, شباب, is in kilowatt, and this one should be calculated in meter cube per second. So at the end, if you divide this, you will find the unit of this actually is the pressure, which should be kilopascal in this case. And that's why we call it indicate mean effective pressure, or brake mean effective pressure. It is not a pressure, it is just a virtual pressure. If the cycle is performed under this constant pressure, it will result actually in the same work in it like the actual cycle. We have two definitions: indicate mean effective pressure, indicated power divided by V dot displacement, and the brake mean effective pressure, which is brake power divided by V dot displacement. And how we can relate them with the mechanical efficiency? If we divide both of them, then it will equal to the mechanical efficiency will equal to brake mean effective pressure divided by the indicated mean effective pressure in this case. Type we have defined the difference between brake power and the indicated power as the friction loss power. So we said indicated power will equal to the brake power plus the friction power. If I divide by V dot displacement here, so this will be indicate mean effective pressure will equal to the brake mean effective pressure plus the friction mean effective pressure. And the friction mean effective pressure is equal to the friction power divided by V dot displacement in this case. Okay, so we can relate the friction losses in terms of the friction mean effective pressure, and in this case it should equal to the indicate mean effective pressure minus the brake mean effective pressure in this case. Okay. This parameter يا شباب indicate mean effective pressure is representing, or the mean effective pressure in general is representing the net work out of the cycle per unit displacement volume. That means it is independent of the size of the engine, and that's why we can compare two engines of different displacement in terms of this parameter, which is the mean effective pressure in this case, because it is independent of the displacement volume. طب look at the definition here يا شباب. If you look at this definition, indicate mean effective pressure is indicated bar divided by V dot displacement, which is V displacement pi over 4D square L multiplied by N over I by 60, which is the number of cycles per second. You can just rearrange it, then we can say the indicated power will equal to the indicated mean effective pressure multiplied by all of this term. It can be represented this way as function of the engine RPM. But this engine RPM, we can define it in terms of the average piston speed, which is a constant value or average value. So we have piston speed, mean piston speed S is equal to 2Ln. Then in this case, we can just replace it in the RPM of the engine to make this term indicate mean effective pressure or indicate power as actually not in, or as independent term actually of the engine RPM. So we can represent the indicate power will equal to the indicate mean effective pressure multiplied by the displacement volume, which is the area of the piston, pi over 4D square multiplied by L. L is the stroke. L and N, we can replace them with the average piston speed, so we can just left actually with this equation. If we look at this term here, it is independent of the engine displacement and also independent of the engine RPM. Like this, we can define the brake mean effective pressure, which is the brake bar divided by V dot stroke. Brake bar is torque by omega. Omega is 2 by N. N will go with N, and at the end we can define the brake mean effective pressure as function of the torque and the function of the displacement volume in this case. Per unit displacement. That means it is independent of the displacement volume. That means this parameter, which is the mean effective pressure, is independent of the engine displacement and also independent of the engine RPM. That means actually we have more freedom in this case to compare different engines. And this parameter is more effective parameter in comparing two engines than the torque. So usually if you went to the market, try to get a car, he will give you this car can provide a torque at a given RPM. And this torque is higher than actually the torque for another car, another given car. This torque torque is equal to what? Or brake power is equal to torque by omega. So the torque engine size, which is the displacement of volume. As the engine size increases, the torque will be increasing in this case. So torque is function of, is independent of engine RPM, but it is function of the engine displacement. This is the torque. Brake mean effective pressure, as you can see from this equation, it is per unit displacement volume. That means it is independent of the engine displacement, the engine size, and also it is independent of the engine RPM. So when you compare actually two cars or two engines, I think it is more realistic. I'm not thinking this is actually the clear reality that to compare the two engines, you should not compare the torque. You have to go for the comparison of the brake mean effective pressure because it is independent of the engine RPM and also independent of the engine displacement. So let's look here at the same RPM. If we have two engines of the same displacement volume at the same RPM. So higher maximum mean effective pressure, brake mean effective pressure, that means actually the engine of higher brake mean effective pressure, this engine is producing more work. So at the same displacement, if you have two engines with the same engine CC, like if we have Toyota Corolla, this is 1.6, and we have also Nissan Sentra, it's 1.6, the same engine size, same displacement. If they are running at the same speed, then in this case, the ones that have higher brake mean effective pressure should have the higher torque in this case. Because we said, Shabab, the brake mean effective pressure is the pressure that can produce the same work in it. So if the mean effective pressure is high, that means actually the net work is high. Net work is high, that means the torque is high in this case. But when we compare the torque is actually depending on the engine size. So it is misleading in this case, unless they have the engine size, the same engine size, same engine CC. طب at a given RPM for the engine torque, if the two engines have the same torque at the same RPM, then the ones that have higher brake main effective pressure should have a smaller engine displacement, because the brake main effective pressure is the brake bar divided by the displacement volume. And the brake bar is equal to torque by omega. At the same RPM, if they have actually the same power, that means actually they have the same torque. So that means actually the engines that have higher brake main effective pressure is having lower displacement volume, which is a compact size engine. Okay, so if we have two engines that have the same torque at the same RPM, same torque at the same RPM, that means the same brake power. So the engine of higher brake main effective pressure should have lower displacement volume. It should be of compact size. And this is a bonus for the engine. Like the case of supercharged and turbocharged engine. It can increase the brake power of the engine for the same engine displacement. So the engine is running under high pressure and high temperature. But there is a drawback for this case that running the engine under high pressure and high temperature should just shorten the lifetime of this engine. So if you have supercharged car or turbocharged car, usually the lifetime should be actually less than the case of naturally aspirated engine. And that's why I told you earlier, if you are just to buy a used car or something, if it is super or turbocharged, just look at actually about the usage of this car, the time actually, or how long actually this car has been in service. Okay, because if it has been in service for a long time, that means actually we are not actually left with more time with this car. يعني this يا شباب as I told you also شباب, in case when we have supercharged or turbocharged car, when there is a problem in the supercharger or the turbocharger, we have to fix it. We cannot just remove the turbo or supercharger and the car will be running or the engine will be running. No, we have to fix it in this case, or we have to replace it. And actually turbocharger and supercharger, they are of high price. Okay, طيب usually شباب when we start designing a car or engine, usually we have those values of highest or maximum brake main effective pressure are already defined for a spark ignition engine and also for diesel engine. If you look here شباب, for a spark ignition engine, usually they have higher brake main effective pressure than the case of diesel engine. But why is that يا شباب? Why spark ignition engine have higher brake main effective? Exactly, Ali. So this is related to the engine side. In case of compression ignition engines, the engine size is bigger, so the displacement volume is bigger. That means the brake main effective pressure will be reduced, which is defined as the brake bar divided by the displacement volume. However, يا شباب, in case of compression ignition engines, the pressure inside the cylinder should be higher, and it should be resulting at the same RPM should give more power, more brake power. But the brake main effective pressure is the brake bar divided by the displacement volume. Usually, diesel engine are bulkier engine, have higher size, so the displacement volume for the same power output or the same RPM should be bigger in case of diesel engine. As I said, in case of diesel engine, the stroke of the engine, the height, the distance between the top dead center and the bottom dead center should be high in order to have enough time to have the expansion of the full expansion of the high pressure inside the cylinder until we reach the atmospheric pressure during the exhaust system. So usually when you start designing a given engine, you will start with the assumption of the brake main effective maximum value of the brake main effective pressure that you can start with. Let's say the brake main effective pressure is equal to 800 kilopascal, and in this case I will start the calculation in order to estimate the engine size, the engine displacement volume that can give me actually a given value of torque or power at a given specific RPM. So all of the calculation of the engine should be at a given RPM. When you change the RPM of the crankshaft, all of the calculation will be changed in this case. Even at the design stage, when you design an internal combustion engine, I will start with the assumption of brake main effective pressure. Then I will calculate the engine size in terms of the displacement volume, the size of the piston, diameter, and the stroke in order to provide me a given power or torque output. I need this engine for this car to provide a given torque or a given power at a given speed RPM. So I will start with this assumption, brake main effective pressure, and calculate the engine size, and then we can move on. يعني just design stages يا شباب have many يعني trial and error يعني you have to go back and go back and forth until actually you just finalize the design. Okay, so it's not يعني just an easy process. Here يعني for يعني this is all the version car 1998. You can look here يا شباب in the specs of any car like the Mazda Millenia S. This is actually a turbo car. This is the engine type L4. That means we have inline engine. We have 4-cylinder engine arranged in line with each other. Here we have different car of V-type engine, and for each engine, شباب, it should give you the displacement volume, which should be شباب, the engine CC, what we call the engine CC, which is the displacement volume by over 4D square multiplied by L for each cylinder multiplied by the number of cylinders. Also, in the specs of an engine, it should give you the maximum power and at which RPM. Look at this curve يا شباب here. Maximum power can be obtained, or the maximum rated power can be obtained at a given RPM, and this value will be different from one car to another. Running the engine higher than this RPM will result actually in decay or degradation actually of will result actually in reduction of the brake power output of the engine in this case. So this is the maximum rated power at 5,300 RPM. So if you went above this RPM, the brake power will be reduced and it will not be increased in this case. Here يا شباب the maximum torque. Also the maximum torque can be obtained at a given RPM. Okay. Usually the maximum torque is obtained at lower RPM. Okay, at lower friction losses. If you look here on the same figure, performance curve, here is the maximum torque. Maximum torque usually obtained at almost 4,500 RPM. We can get the maximum torque of the engine. The maximum torque is important in some situation. I have written it somewhere here. Here. The torque is important in some situation, like if you go just going uphill, just driving actually to go through a mountain or something. So in this case, you have to be driving the car near the maximum torque condition. Maximum torque, you can look at the specs of the car, as you have seen here. You can look from the performance curve where I can get the maximum torque of the engine. It should be at this RPM, 4,500 RPM. So if you are interested in التفحيط or something, so you have to run actually at this. You have to run at this RPM. If you are going uphill, going up to a mountain, you need torque in this case. You don't need much power, but you need torque applied on the crankshaft. Okay. If RPM also, if the engine is running at fixed RPM, like in case of electrical power generation, if we have a diesel engine in order to be connected to an electric generator to generate electrical power, in this case, it has to be running at a fixed RPM, and we need in this case the maximum torque, and we have to run the engine at the maximum torque. And this is related to the application, شباب. If you are in your inshallah and your work after graduation, if you are actually to deal with an internal combustion engine, diesel engine, in a far field to generate electrical power, usually if we are just in a zone in which you don't have access to the network, the electrical network, we can use diesel engine and connect it to an electric generator to generate electrical power. In this case, شباب, this diesel engine has to be run for the maximum torque. So it has to be running at the RPM that can generate the maximum torque in this case, in order to be working efficiently. Okay. Also, when we have a moving object from the rest, if you just need to move something from rest, like the first gear in your car, if you have manual car, or even if you have automatic car, but you are moving from rest. So once you start moving the car, you need the maximum torque in this case. But in this case, we cannot run the engine at this RPM, 4,500 RPM, that the car will be just flying. But this is one of the situations that the engine need higher torque in this case. So the higher torque, the maximum torque is defined at a given RPM. If you just go to a mountain, just running the engine, the car actually to go uphill in a mountain or something, or a high inclination of the road, in this case you can run the engine at the RPM that can produce the maximum torque, because I need torque in this case. We define also the brake mean effective pressure يا شباب. Also all of the terms يا شباب we have indicate and brake. But when it comes to comparing the different car, it will be talking about the brake because it is the final outcome. So here it is talking about the brake mean effective pressure at the maximum braking torque and the brake mean effective pressure at the maximum or the rated power in this case. All of these specs يا شباب should be given for the different cars. يعني by which we can compare which car actually or which engine is much better than the other engine. Okay. طيب here شباب is engine balance. I don't think يعني we have time to go through that. So let's leave this يعني to the next time inshallah and we'll try to solve some problems inshallah. طيب do you have any question يا شباب؟ يعني by this يا شباب يعني I'm just left with the engine balance here يعني nothing new يعني just the incoming energy is equal to the outgoing energy based on the first law analysis. We can do this balance and then actually if we have the brake power is given we have mass flow rate of the exhaust cooling water then we can calculate the free anyway يعني this is inshallah we'll be talking about but we don't have something new يعني inshallah next time we are done with all of the equation, all of the performance parameter. Just next time, inshallah, I will show you how to link this with the cycle analysis that we have learned from chapter 5, how we can start from the intake engine condition, intake engine pressure, intake manifold pressure and intake manifold temperature, how we can go with the solution, like what you have done in the last homework. You have went with the solution until you have calculated the indicated power of the engine. And you calculated the indicated thermal efficiency. From this point, شباب, we can link it with the performance parameter that we have learned today. From this indicated thermal efficiency, we have already calculated the indicated power. And from the indicated power and the mechanical efficiency, we can calculate the brake power. Okay, brake power is torque by omega. At a given RPM, we can calculate in this case the torque of the engine. And at each RPM, we can calculate all of these parameters. Then we can plot the performance curve. The performance curve should give us the brake power and the brake specific fuel consumption as function of the engine RPM. And then we can plot this map. Getting this map, we can store it on the engine electronic control unit, engine ECU. So at a given loading condition, at a given RPM, the engine already actually knows about the amount of fuel that should be injected in this case, about the timing of the exhaust valve, when it should be open in order to have the exhaust gases released in this case. So everything should have been calculated before running the engine of your car. Usually the engine knows actually all of the operating conditions. They are stored. And he knows actually once you press on your leg and the accelerator pedal, depending on this press, the engine is able to calculate everything for your car. Okay? And all of this data, shabab, has to be calculated before releasing the car or putting the engine into a car. All of this data has to be calculated. And that's why, shabab, the car are of high price. This high price is not coming from the material of the car. It's coming from testing this car, this engine actually at all possible operating conditions. We have to test the engine, measure all of the data, record all this data into the electronic control unit of the engine. Then once you press on the accelerator pedal, actually the engine knows what it should to do actually, and how the engine should be working in this case. So those tests usually cost, and that's why the car are still of high price. After all of these years of service, still the car prices are still high. Because once we have any improvement in the car, we have to repeat actually all of this tests, okay?